Hello, this is the first video covering material out of section 10.3 in our text, where we're talking about looking at convergence and divergence of series with positive terms, specifically the integral test and comparison tests. This video will deal with issues arising from the integral test. So before I begin working examples, just a verbal reminder of what the integral test is. You have a function which takes on only positive values, is decreasing and continuous for x bigger than a certain number. Often it's 1, not always. We can use 2 or 3 in particular examples. And another important thing is that when you plug integers into the function, you get the terms of the series that we're trying to sum to see if the series converges or not. And so what the integral test tells us is once we have such a function and we evaluate the improper integral of that function, often from 1 to infinity, but occasionally over other ranges, whether or not the integral converges tells us whether or not the series converges. And so I want to look at a couple of examples where we apply the integral test in reasonable detail, and then we'll also look at an example involving estimating sums of series using the integral test remainder. Our first example, summation n equals 1 to infinity 2 over n to the 4/3, is a multiple of a p-series. And if you've read the section, you know that we actually know the story about p-series already, and that a p-series converges when p is bigger than 1. It diverges when p is between 0 and up to 1. And here our value of p is 4/3. And so we know already, since that's bigger than 1, that this series is going to converge, but I want to go through the steps of the integral test to verify this. So what we want to do is we want to take our function to be 2 over x to the 4/3. So we note that f of x is bigger than 0 when x is bigger than 1. We plug a positive number in, the 4/3 power of that positive number is a positive number, 2 over a positive number is positive. Decreasing, to show decreasing, we should look at the derivative. And so our derivative is going to be, I believe, negative 8/3 x to the negative 7/3, which I could rewrite this way. And we observe that this is less than 0 for x bigger than or equal to 1. So f is decreasing. And it's continuous. The only hole in the domain is at 0. And we're excluding that point from our consideration here. So looks like our function passes the test, and so what we do then is we look at the integral from 1 to infinity 2 over x to the 4/3 dx, which I should write as the limit as t goes to infinity 1 to t, and I'm going to go ahead and write this with a negative exponent to allow me to think about what the antiderivative is more quickly. When we antidifferentiate, my new power is going to be negative 1/3. 2 over negative 1/3, I believe, is negative 6. So I evaluate. And I get plus 6 when I plug in 1 there. And I've left off the negative 1/3 there. So I've got, maybe I should rewrite it this way. as t gets big, then my denominator is going to get big, and so this is going to go to 0, and so I get 6 out. And so the integral converges. So by the integral test, my series converges as well. Our next example is a sort of a classic of the genre, summation n equals 2 to infinity 1 over n log n. We're not starting at 1 this time, and that's because the natural logarithm of 1 is 0, and so this is undefined for n equal 1. So I'm going to let f of x equal 1 over x natural log of x. This is, so natural log of x is positive for x bigger than 1. And so 1 over x log x is positive for x bigger than or equal to 1. And, sorry, 2. We're interested in 2 here. To show it's decreasing, well, let's think about this. I could use the quotient rule if I wanted to. That's going to be the derivative of the numerator, which is 0, times the bottom, which just is going to be 0, minus the numerator times the derivative of the denominator. We use the product rule for that. And so I'm going to get natural log of x plus x times 1 over x. So that's going to give me natural log of x plus 1 squared. So I get a negative number over a positive, and so it's going to be less than 0. So this function is decreasing, and we've already commented that the function is going to be continuous for x bigger than or equal to 2 because the function is defined for numbers bigger than 1. So we're going to look at the integral from 2 to infinity of 1 over x natural log x. Hopefully you recall that we need to use a substitution to integrate this. And so when x is equal to 2, u is going to be natural log of 2. When x is equal to t, u is going to be natural log of t. So if I had written this step first, now after I substitute, it's going to be the limit as t goes to infinity, integral from natural log of 2 to natural log of t, 1 over u du. And so integrating that, we get natural log of u, evaluated between natural log of 2 and natural log of t. And so I get limit as t goes to infinity of natural log of the natural log of t minus the natural log of the natural log of 2. And as t gets big, log t gets big, and so the natural log of the natural log of t is also going to get big. This is going to be going to infinity. And so this integral diverges. So by the integral test, summation n equals 2 to infinity 1 over n log n diverges as well. Last thing on this video I want to do is I want to do another example where we approximate the sum of a series, a convergent series, using a remainder estimate. And so if you've looked at the notes from this section, we want to realize that the remainder of this series is less than the integral from capital N to infinity of 1 over x to the fifth dx. And we know that this is a convergent series. It's a p-series with p equal to 5, which is bigger than 1. And so if I want to make this less than 1/20,000th, I'm going to do a little bit of overkill, and I'll make this true, so that if this is less than 1 over 20,000, then definitely, so if this is less than 1 over 20,000, since this is bigger than my remainder term, this remainder will also be less than 1 over 20,000. So let's evaluate the integral. Again, we write this as a limit. So anti-differentiation is not difficult. It's negative 1/4 x to the negative 4. As t gets big, that goes to 0, so the value of my integral is 1 over 4 n to the fourth. And so we want to find n so that 1 over 4 n to the fourth is less than 1 over 20,000. Well, if I just take reciprocals, I change the direction of the inequality. So that means that 4 n to the fourth is bigger than 20,000. If I divide by 4, I get that n to the fourth is bigger than 5,000. And so I want to take n to be bigger than 5,000 to the 1/4. And when I plug that into my calculator, I get that to be about 8.4. So we'll take n to be any number bigger than 8.4, which will go with the least resistance, and say n equals 9. And so then what we've discovered is, if I just add up the first 9 terms of this series, this is going to approximate the sum of all terms of this form to within 1/20,000th of its value.